Right, so this is the last video of paper one. This is atomic structure. Hopefully for the combined students this will be less than 10 minutes. Fortunately for the separate students it's a bit longer at the end. Okay. Right, so let's get going. So atomic structure. So the first thing you need to know is that atoms are very small. They have a radius of about 1 × 10 to the minus 10 meters. Okay, so very small. Now a nucleus is much smaller than that. That's 1 × 10 to the minus 15 meters radius. So you see there's a factor of 1/10,000 difference between the two. Okay, so that tells you that the atom is mostly empty space. We'll come back to that in a minute. You need to understand what is meant by this kind of notation. I've just used X to represent any element, and we've got A and Z. A is our mass number, and that is protons plus neutrons, so those two added together. Z is the atomic number, and that is just your number of protons. So if you want to work out the number of neutrons, you just subtract Z from A. Okay, now for each element, or for lots of elements, there are isotopes. Now an isotope is an atom with the same number of protons but a different number of neutrons. Okay, and what we're going to see in a little while is that some of these isotopes are actually unstable, which makes them radioactive. Okay, so the other thing we need to know is how the model of the atom was developed, and this is common to chemistry. So we'll start with Dalton. He came up with this idea of these indivisible spheres. So if you took some gold, for instance, and kept chopping it in half and half and half and half, eventually you'd get to the point where you couldn't chop it in half. So that would be like an individual little bit, indivisible bit of gold. Now, what happened after this was they discovered the electron, so I'll put J.J. Thomson here. They discovered the electron, and then this plum pudding model was the model that everyone agreed upon. So this was the idea that the atom is a ball of positive charge with little negatives dotted throughout it, like the plums in a plum pudding. Now after this, Rutherford and his students, they performed an alpha scattering experiment. This disproved the plum pudding model. I'm going to go on to that in a little while. And I'll tell you the findings of that. So this disproved this plum pudding model, and the model had to change again. There then came Bohr, who came up with this sort of planetary model with the nucleus at the centre and the electrons orbiting in shells. Okay, so you can see that over time, scientific theories have to change because new evidence is discovered that isn't explained by the current theory. So theories develop over time. Now, if we just talk about this alpha scattering, that symbol means alpha. So alpha scattering experiment, there were 3 findings. Number 1, most alphas passed straight through, as in they were undeflected. Now what this told us, I mentioned this just a minute ago, is that the atom is mostly empty space. Okay? Number 2 was that some alphas were scattered through small angles. Now what this suggested was, because the alpha is obviously a positive particle, this suggested that there was a positive charge at the centre of the nucleus, centre of the atom. All right. Now the third finding was that very few alphas scattered through large angles. And what we mean by this is that they kind of like head-on collision and they come back at you, so large angles. Now, if they're only doing that very, very infrequently, that tells you that this positive charge is very small. So we'll say it's concentrated in very small volume. And what that means to say is that the nucleus is very, very small, and we've seen that up here. Okay, so I'm just going to put at the bottom a little time frame, because electrons were what were discovered first, if you think about this plum pudding model. Then they discovered the nucleus in this alpha scattering experiment. Then protons were discovered. You don't need to really understand or know who and why protons were discovered. But then after that, they discovered neutrons, and that gives us the model that we've got today, and this was done by Chadwick, a guy called Chadwick. Again, you don't need to know the details of that, but you do need to know his name. All right, so yeah, moving on. I mentioned here about these isotopes, and some isotopes are unstable, and that means that they decay. So I'm just going to write that here. Some isotopes are unstable and decay. Now they decay to try and become more stable, but this decay is random. Oh, random. That means you don't know which one's going to decay next. The units for activity or radioactivity are becquerel, and we can measure it using a GM tube. Now this is called a Geiger-Muller tube, but if you put GM tube, you'll get the marks. And there are 3 types that you need to know. So the first one, I'm going to make sure I've got enough space here. So alpha. Now alpha you'll see written like this, 4,2, and then that symbol that we've seen already. Sometimes you see it written like this, 42He, and people say that it's the helium nucleus. Okay. Now an alpha is 2 protons, 2 neutrons. That means it has a quite large mass compared to the others, and it has a +2 charge because it's got those 2 protons. The properties of this is that it's highly ionizing, and it's got very low penetration. Now you think about this +2 charge, as it passes into a material, it's able to rip the electrons from the atoms in that material. That's why it's highly ionizing. Each time it does that, it loses energy, so it doesn't get very far. The penetration is kind of how far into that material it gets. And this will be stopped by paper or a few centimetres of air. The next one is beta. Now this has the symbol 0, -1, and then this B. Sometimes you see it written like this for an electron. And that's what this is. It's 1 high speed, sorry, this is a bit cramped, electron. So this has a fairly low mass, much lower than the alpha, and it's a -1 charge. So -1 charge, lower mass, that means it's kind of like less ionizing than alpha, and it'll get a bit further, so it's kind of in the middle. And it's stopped by aluminium and a few meters of air. The last one that you need to know is gamma, and this has the symbol 00, and then it's kind of like the alpha symbol turned through 90 degrees, and this is high energy EM radiation, EM for electromagnetic. So what that means is this is very different to these two because these have mass, this doesn't. These are charged, this isn't. So we would say that it is massless and chargeless. So this is just like energy. These two, alpha and beta, will change the type of isotope you have, the type of atom you have, because you're changing your atomic number, your proton number. This one doesn't. So you have still the same thing, but it just has less energy. And what we'll say here is it's low ionizing, weakly ionizing, however you want to say it, but it's got a high penetration. So it will get very far into a substance. And for this, you need thick concrete or lead to stop it, and it will travel a few kilometers in air. Okay, so that's alpha, beta, and gamma. Now, the next thing we're going to talk about is half-life. So I'm just going to draw a quick graph, but I'll give you the definition first. So half-life is the time taken for half the nuclei in a sample to decay. Okay, now you'll usually see a graph for this, and the graph will look something like this. And if this is how many you've got at the beginning, let's say that's 80,000, obviously after one half-life, you can have 40,000. So we'd find 40,000 on the graph. I've not drawn this very well, but you'd read across. When you get to the curve, you read down, whatever that is, that's your half-life. So yeah, I've not drawn that very well, but that's the process. Half the initial number, horizontally across and then vertically down. Now, for separate, you will need to be able to also understand this in terms of percentages. So after one half-life, it'll be 50%. After another half-life, it's going to be 25%. Another one, 12.5, 6.25, and then 3.125. And you can see that is 1, 2, 3, 4, 5 half-lives. So they might say, how long does it take for the sample to fall to 3.125% of its original? And that is 5 half-lives. If it was, let's say, 100 years, 5 half-lives times 100 years is 500 years. You also need to be able to do it as a fraction. So this one's a bit easier probably. 1/16, 1/32, but you can keep doing that. And you can see that's 1, 2, 3, 4, 5 again. Okay, lovely. So that is half-lives. I'm just going to move on quickly and talk about some nuclear equations, because when you've got these alpha, betas and gammas, when things decay by alpha, beta or gamma, you need to be able to work out what the mass number or the atomic number of the new thing formed is. So let's say we've got uranium, 23892U. Let's say this decays by alpha. So we're saying 42 alpha. Now our unknown substance here, you would have to be able to work out what its mass number and its atomic number are. Well, for the mass number, I need something that when I add it to 4, I get 238. So that's going to be 234. And for the atomic number, I need something that when I add it to 2 gives me 92, so that's 90. And then if you've got a periodic table, you'll be able to identify that. Usually they'll give you this symbol. Now, it's not always these two numbers that they ask you to calculate. They might just have this one missing or this one missing, and you've got to fill in the gaps. But it's just adding up the right-hand side and the left-hand side to make sure they're equal. If we do a quick beta, so let's say it decays by beta, this one's a bit tougher. Let's put X again here. So now this top one is a bit easier because I need something that when added to 0 gives me 14, so that's obviously 14. But on the bottom, I need something that when added to -1 gives me 7. Okay, so something -1 gives me 7. That's going to be, oh, sorry, I put 7 there. That's a silly Billy. That should be 6. So this should be 7. My bad. And then if we just take uranium again, let's say uranium 92, and let's say this decayed by gamma. Like I said earlier, you can see that this is just going to be uranium again because the numbers don't change. Okay, lovely. So, right, that's that. Last two things for combined, and this is higher only. We've got two things called irradiation and contamination. Okay, so irradiation is exposure to radioactive particles, decays, yeah? Radioactive particles. Now, contamination is different. Contamination is the unwanted presence of radioactive material. So this is when the actual radioactive material is on you, or even worse, inside of you. So for irradiation, you can just shield yourself, you could remove yourself from the source, get some distance between you, and you would stop being irradiated. But contamination, if it's on or in you, we have to either wash it off of you, if that's possible. But if it's inside you, it's very difficult to get rid of. And you kind of just have to wait it out until enough half-lives have passed that it's not radioactive anymore. And that's when it becomes very dangerous. Okay, right, so that is the combined stuff done. So this bit in the top, which we'll put a little box around this is going to be the separate only stuff. So we've got background radiation. Background radiation is the stuff that's all around us, and we've evolved in this. So the biggest one really is radon gas, which comes from the ground. There are other rocks that have radioactive isotopes in them, and they will emit radioactivity. We've also got foods. We've got cosmic rays from space, and we also have sort of like human activity. So that could be medical, it could be weapons testing, it could be actually dropping weapons, and it could be accidents like Chernobyl, which we've talked about in the lesson. Okay, so yeah, that's background radiation, don't need to do too much on there. The next two things I want to talk about are fission, which remember means splitting, and fusion, which means joining. So if I just draw a little diagram here, this is a neutron. This needs to be absorbed by a large nucleus. Let's say this is uranium-235 or whatever. Once this neutron's absorbed by this, it's going to make an unstable nucleus. So I'll put U-236. So this is going to be unstable isotope, because remember it's changed the number of neutrons. And what that'll do is it'll split into two smaller nuclei, but we'll also have 3 other neutrons released and energy. Sorry about that. So these 3 other neutrons can go on and cause other reactions, so you can create a chain reaction, and it can get out of control, which would actually cause to a runaway, kind of like a bomb. But this energy that's released, that's what we harvest in nuclear power stations. Now, fusion joining, you have to take 2 small nuclei, and these will join to make a larger nucleus. So we've got 2 small nuclei, and then a large nucleus here. And what happens is, in doing so, and fusing these two and joining these two to create this big one, some of the mass here is converted to energy, and you're probably aware of that equation, E equals mc squared. You don't need to know this for your exam, but some of the mass is converted to energy and it's released as gamma photons. Okay? Now, the only other things I wanted to talk about, and I've run out of space a bit, so I'll just go on to the back, is when we use radioactive isotopes as medical tracers. So this is where we purposefully contaminate a person with a medical tracer, and it usually attaches to a protein, finds its way to a part of the body that they want to image, and we image the radioactivity that it's emitting on the outside of the body. So this needs to be a gamma emitter, so that it can penetrate all through the body and we can detect it on the outside. And its half-life needs to be about 6 hours, something like that, because you want to have enough time to be able to carry out the experiment, collect the data that you need to collect, but you don't want it to be too long that it's causing unnecessary damage. Now, the only other ones, industry. So in industry, we have certain applications whereby the thickness of paper or the thickness of aluminium, so I'll write that down, thickness of aluminium is monitored with a radioactive isotope and a detector on the other side. So obviously if that thickness increases, your count rate is going to drop. If your count rate drops, what will happen is the system will detect this and it'll put the rollers that are rolling out these sheets of aluminium or paper closer together. So this needs to be a beta source, because if it's alpha, it's just going to be absorbed and you won't get any count rate. And if it was gamma, the majority are going to pass through regardless of the thickness. So you need beta that's going to respond to that thickness. Now, if the thickness got too small, the count rate would really drop. That would mean that the rollers would detect it and move further apart. Okay, but we can talk about this more in lesson. Right, lovely, cheers.